Yeah. So I hope you all can see my screen. I have there's a presentation here. Okay. Yeah. Let me keep in full screen mode. Yeah. Good evening to all the students. So welcome back to our NPTEL live session number 2. So this week we will be discussing the week 2 contents. So whatever we learned in this week 2 regarding the transformers, hysteresis loss, Eddy Currents loss. Actually, there has been 2 different sessions in the same day. So for that purpose, what we planned was we have splitted our concepts which we will be discussing in the session. So whatever concepts we discussed right now won't be repeated in the later night session around 7 to 8. You are having another session, I suppose. So yeah, you will be having a different discussion there. So please do join that session as well. So to cover more topics which we discussed today. Yeah. So yeah, moving forward. So let's start with discussing few questions on hysteresis loss and eddy current loss. So we have a question here. We can see we were given with a 400 volts 60 Hz transformer. It is having 700 watts hysteresis loss and 380 watts eddy current loss. It was all under rated conditions. Now we were given with a Siemens constant 1.6, and we were also given a hint that our hysteresis loss is proportional to 5 max to the power of 1.6. So 5 max here is the maximum flux, that the flux that is produced inside the transformer core. And our hysteresis loss is proportional to the power 1.6 times the power of the maximum flux. Now what we were asked is we have to estimate this hysteresis loss in watts if our transformer is operated at 260 volts and 50 Hz. Now if we see the question, initially our transformer is being operated at 400 volts and 60 Hz. But now we have changed the operating voltage and we have changed the operating frequency as well. The supply frequency is also changed. Now when we change the voltage and frequency, how the hysteresis loss and eddy current losses are going to change? Now indirectly we are being asked how the losses will be dependent on voltage and frequency. So that's what we are asked. So before going to solve this question, can anyone tell me what is hysteresis loss and what is eddy current loss in a transformer? Any idea like what is hysteresis loss and what is eddy current loss? Anyone? Let me see. Okay, Ranjit, you are saying something, but I'm not able to hear you. I think some issue with the mic. Whenever I started the recording, I'm not able to hear you. Can you type it in the chat box? I'm not able to hear you, Ranjit. So there seems a problem with the microphone. I can't hear you, Ranjit. Can you type it in the chat box? Okay, I can't hear you. So unfortunately, I can't hear what you are saying. So yeah, we will see a quick. I will just give an introduction, like just a brief introduction of what hysteresis loss and eddy current loss is. So we see we have, let's say we have a ferromagnetic material, so that it can be able to experience a magnetic field. Now, when we place a ferromagnetic material in a magnetic field, and now we are trying to change this applied magnetic field. Now, when we are trying to change this applied magnetic field, the molecules inside that ferromagnetic material will try to align in the direction of that particular applied magnetic field. Now, yeah, so let's say we apply an alternating magnetic field. Now, this alternating magnetic field will change its direction for every cycle, right? So, during this cycle, whenever the direction of magnetic field changes, the molecules inside that ferromagnetic material will try to align with the applied magnetic field direction. So, This is just a process. We have not come to hysteresis yet. Now, when this kind of procedure is happening, now it can result in a kind of loss. How it will result in loss? That is, this is because whenever an alternating current means it will change its direction. Whenever the supply, whenever the direction changes, the direction of current flow will change, the direction of magnetic field will change. Now, when this alternating current changes its direction, the flow will change. Now, therefore, the direction of magnetic field will change because that magnetic field is produced by this particular current. So, whenever the magnetic field changes, this particular change in the magnetic field will force whatever the molecules are present inside the core. So, what it will do, it will force the molecules to change their alignment in the proper direction. So, whatever direction our magnetic field is, that force will that will force the molecules to align with the direction that is the magnetic field has changed. So yeah, so during this movement of this particular molecule's direction, what will happen? These molecules will collide with each other. When molecules will collide with each other, there will be a friction and there will be a heat generated, and due to this friction and heat, there will be energy loss. So this loss is called hysteresis loss. So this is what a hysteresis loss, or this is how we experience a hysteresis loss. So Ranjit has typed something: hysteresis loss and eddy current losses due to iron and copper losses in transformer. No, it is not defined in that way, Ranjit. You are saying the content, like finally what happens, which is proportional to loss. But you have to tell the cause of this loss. What actually is causing the hysteresis and what actually is causing the eddy current loss. Yeah. Now, yeah. Anyone tell me what is eddy current loss? So what are these eddy currents which we talked about, and any idea why these eddy currents will cause us the loss in the transformer? I can't hear you, sir. I think, can you type it? Because while I'm recording, I'm not able to hear. Sorry, sir, I can't able to hear. Can you type it in chat box, if possible? Leela Kumar, sir, I can't able to hear you. So yeah, I think even if your microphones are on, as I am recording the session, I can't hear the voice in the background. So yeah, please type it in chat box if you are saying something. I'm really sorry, I can't hear. Can someone type it in the chat box? Okay. I'm trying to. Okay, so I'm just explaining what eddy current loss is. So whenever, according to Faraday's law of electromagnetic induction, so whenever a magnetic material is subject to a changing magnetic field, whenever an alternating magnetic field is applied to a magnetic material, there will be a voltage will be induced in the material. So that is Faraday's law of electromagnetic induction. Now, since the material itself is conducting, whatever the voltage that is being induced, the induced voltage will cause some circulating current within the body. Because whenever there is a voltage induced, if the circuit is closed, current will pass. That will cause a circulating current within the body. Now, when these circulating currents pass through the body of the magnetic material, these currents are called as eddy currents. So these don't flow in the main circuit, but within the body itself. These are like a circulating currents. These are unwanted currents. Now, these eddy current will cause I square R loss in the material. So this is what we call eddy current loss. So yeah, this eddy current loss will also result in whenever there is an increase in temperature of the material, this loss will increase. So yeah, so this is more or less the introduction about eddy current loss and hysteresis loss. Yeah. Sure. Sure, Leela Kumar, Mr. Leela Kumar, I'll go slow. Yeah, so let me repeat whatever I have said regarding hysteresis and eddy current. So let's first talk about hysteresis loss. So yeah, whenever a ferromagnetic material, let's take a ferromagnetic material, now place it in an applied magnetic field. That magnetic field must be alternating in nature. Now, when the magnetic field is alternating in nature, the ferromagnetic material will have its own molecules. So, those molecules will try to change their orientation in the same direction of the applied magnetic field. So, for example, when we place a ferromagnetic material in an alternating magnetic field, the magnetization in that material will follow a path, right? So that path will be same as the applied magnetic field. Now, yeah. So when we change the magnetic field, the flow of the path will also be changes. Now, during this path changing, whenever these molecules try to change its path along the magnetic field, they will start to collide with each other. So these molecules will collide with each other, and that will cause some friction and some heat. So yeah, whenever the friction whenever this friction happens, whenever some heat is produced, so yeah, there will be energy loss. So this is what hysteresis loss is. Yeah. So let's now start to solve this question. Whatever we see. Yeah. Let's write whatever data was given to us. Okay. Okay. Yeah. V1 is equals to 400 volts. F1 is equals to 60 hertz. And yeah. Now V2 is equals to 260 volts. And F2 is equals to 50 hertz. Now, yeah, we have two different sets of operating voltages and frequencies. Now, let's write PH1, that is 700 watts, that is hysteresis loss, and eddy current loss, let's represent as P1, that is 380 watts. Yeah. So now we were asked to find the hysteresis loss in the transformer if it is operated at different voltages. Now whatever is required, what is required here? PH2 is equals to N. This is the question. We need to find the hysteresis loss in the transformer if it is operated at different voltages. Now let's write the formula of hysteresis loss. PH is equals to, there is a hysteresis constant KH and frequency, it is B max over N into the V. Now here the KH, KH is the hysteresis constant, F is the frequency of the input supply, and B max is the maximum flux density, and here the N is the constant, and this is the volume of the core. Now here N is given, this is as 1.6. Now N is equals to 1.6. Yeah. Now we know that B max, this is phi max divided by area. Now this B max is Weber per meter square, and this is the maximum flux that is produced, and divided by area, this is flux. Now yeah, since the area is constant, we are not changing the transformers, we can directly replace B max as proportional to phi max. Now we see PH is proportional to, KH is constant, it's not proportional, KH is proportional to frequency, and B max we can write it as phi max by area, and since area is constant, phi max power N, and yeah, volume, same transformer we are using, so there will be no change in the volume of the transformer. So these two, pH is dependent on these two factors, that is frequency as well as maximum flux produced. Now N is equals to 1.6 here. Yeah. Now we have to find a relation between frequency as well as voltage, because these two are the changing contents here, the operating conditions. Now we know last week we discussed the induced EMF equation, that is E is equals to 4.45 ft. Yeah. So here we have to bring a relation between voltage as well as frequency, right? Now in this equation, if we see, this flux is proportional to V and frequency and this T. If the thickness is constant, thickness of the transformer laminations will be same every time. So yeah, now flux is proportional to E divided by F. Yeah, now we will replace this particular relation here. Now let me take another sheet. Now pH proportional to F into, we will replace the maximum flux by the voltage divided by frequency. V divided by F to the power of 1.6. Yeah. So pH1 by pH2 is equals to, if we F divided by 1 minus 1.6 into voltage power 1.6. Now, yeah, please calculate this. F1 minus 1.6 into V1 1.6 divided by F2 divided by V2 power 1.6. Yeah, now we were asked to find this pH2, what will the second hysteresis loss if the transformer is operated at this 2 V2 and this is F2. Now we know the values of V1, V2. From here we know the values of V1, F1 and V2, F2. Now just substitute here and we will get the value of pH2. Can someone calculate along with me and just give me the answer in the chat box? I will also calculate this. pH1 is 700. We will be multiplying with F2 by F1 into minus 0.6 into V2 by V1 over 1.6. F2 is 50 Hz, 50, F1 is 60, power minus 0.6 multiplied by V2 by V1. How much is second voltage? 260 divided by 400 into 1.6. .55 I got. we have to multiply it with 700. Yeah. Can someone tell me? Okay. No, Ranjit. So I will type the calculation here itself because I got something different from you. Let's see what I got. Now pH2 is equals to pH1 multiplied by F2 by F1 minus 0.6 and V2 by V1 1.6. Now 700 F2 is 50 divided by 60 multiplied by V2 is 260 divided by 400 1.6. Now pH2 is equals to 700 into how much I got? 1.115 multiplied by this something 260 by 400. .501. Yeah, Smith. Yeah, you got close. I got 391. I see you have written 398. 391. Yeah, 391 point. Yeah, something 77 I got. Yeah, that will do. So yeah, 390. Yeah, I am seeing correct answers. Yeah, please try to solve along with me so that we can tally our answers. 390. Yeah, please, rest of the students, you also try to solve along with me. Now we were given with two different voltages, operating voltages and two different frequencies, and we were asked to calculate the hysteresis loss. Now, before going to calculation, we have to understand how hysteresis loss is dependent on voltage and frequency. Now, from the formula, we were able to get the proportionality dependency on voltage and frequency, and we have substituted the different voltages and frequency, and we are able to get the hysteresis loss. Yeah, everyone should get around this answer, 390, 1.77, 390 around. Yeah, that will be okay. Okay. So yeah, the same way we did for hysteresis, let's now calculate the eddy current loss. So I will write the formula for eddy current loss here, and I also want you to calculate along with me. Now eddy current loss is equals to, there will be eddy current constant and frequency square Bmax square and thickness of the sheet, this is T square into V. Now Ke here is eddy current constant, F is frequency, Bmax is the field intensity, and T is thickness of the sheet, and V is the volume of the core. Now again, what are the proportionality parameters here? Ke is constant, this is constant, and yeah, frequency will be dependent term, Bmax will be dependent term, thickness again is a constant, and volume is constant. Now the proportionality variables are F square into Bmax square. Now again we will replace Bmax by flux. Into square into phi max square. Now if we replace this again phi max in terms of voltage and frequency, because that's what variable parameters here, F square into E by F square. Now final equation is PE is proportional to F square into V by F square. F square will cancel. It's proportional to V square. Yeah. So now we see here, actually it is not dependent on frequency. Now even if you operate this transformer in 60 Hz or 50 Hz or any other frequency, the eddy current loss is not going to vary. Now it is actually dependent on voltage here. Now please do calculate how much is that. P1 by P2 is equals to P1 by V2 whole square. Now how much is V1? V1 is 400 volts. Now 260. Okay, something we will get. Now P2 is equals to P1 into 260 by 400 also. Now what is the given PE1? 380 watts. 380 into 260 by 400 square. So can someone tell me how much is the new eddy current loss? Okay, I see some answers coming up. Let me also check with me. How much is this? 380. Okay, it's 160.55 watts. So let's see what answers you are getting. Okay, yeah, Smith, Ranjit Pandey. Okay, Dhanesh ji, you have got a bit higher answer, 900. Please recheck your calculation. Yeah, Shah Tulsi 160. So yeah, it's correct. Please recheck your answer, Dhanesh. It's V1 by V2. So when you take to PE2, it will be V2 by V1. So maybe there you have got mistaken. Just yeah, 160.55. Okay, that's it. That's a simple relation between eddy current loss and hysteresis loss dependency on the voltage and frequency. Now you can able to solve for different voltages and different frequencies, how to approach in solving the question. Okay, please do solve the questions along with me so that you will also get the hang of it. Now let's move to a different question. So the above figures, so we were given a figure here. It is an equivalent circuit of a transformer. The transformer rating was given here 100 by 500 volts, and it's a 50 Hz transformer, single phase transformer. Okay, here we have it is referred to the LV side. The entire equivalent circuit have been referred to low voltage side. Okay, now R0, we have all given the equivalent circuit parameters, R0, XM, RE, XE, fine, and it is being said that the LV side is energized with the rated supply. Okay, and a load has been connected. A load impedance is also given, but observe here the load impedance is connected on the HV side. It's not on the LV side. So that's a point to be noted. Okay, we were given with it. Now we have to estimate the LV side current. Fine. Before solving it, whenever you are solving such kind of questions, LV side and HV side, the first thing you have to remember is if you want to solve for any parameter, refer all the parameters either to LV side or HV side, then do the calculation. Now, if the parameters are like referred to two different sides, you are doing the calculation, you will go wrong, because the parameters, you have to see where the parameter is being referred. Is it on the LV side or the HV side? So if you want to do it on HV side, refer all the parameters to HV side using the turns ratio. We were already provided with the turns ratio, that is 100 by 500, that is the rating of the transformer, and then do the calculation. If you want to refer to LV side, you refer to all the parameters from HV side to LV side and do the calculation. Now, here we are provided with an equivalent circuit which is already being referred to a LV side, and there is a load at the HV side, that is impedance. Now we were asked to calculate the LV current. So first what we will do, we will refer that impedance, load side impedance, to primary side, LV side. There is no primary, secondary, we will call it as LV, HV. Now we will refer that HV side impedance to LV side, and then we will solve for the LV current. So I hope you understood. Now let's see how we can refer the LV side impedance to HV side. So in the last week discussion, we discussed how we transform any parameter to any side. So that is all dependent on the turns ratio. Now let's see here what we were given with. Now turns ratio, we denote it as A. It is 1 by 5. A is 0.2. We keep it aside. It will be useful for us to refer any parameter to any side of the equivalent circuit. Now RL is equals to 50 plus J40. So let's not write it as RL. It is ZL. It's an impedance. It's having both real part and imaginary part. Okay, Mr. Leela Kumar, whatever I'm saying is, so we were given with the equivalent circuit. So it is being said in the question that all the parameters in the equivalent circuit have been referred to LV side, that is low voltage side. So if you see the rating of the transformer, it is 100 by 500. So the LV side is 100 volts and the HV side is 500 volts. Now whether you take a transformer, a motor, or any machine, it will have its own equivalent circuit. So we can depict the performance of that machine, whether it's a transformer or a motor, in terms of this passive components, resistor, inductor, capacitor. We can like the behavior of the machine can be depicted in terms of this passive components behavior. So that's the equivalent circuit means. So now we have an equivalent circuit. All the parameters have been referred to LV side. Okay. Now we were asked to calculate the current. So, but there is a load resistance that is connected on the HV side. So it was given in the question. And if you see the question, 50 plus J40 omega, that's the impedance that is connected to the HV side. Now we were asked to calculate the current. So it's simple. It's a simple network problem. It comes down to a simple networks problem. But the thing is, we were having an impedance which is referred to the load side. Now we have to refer that to the primary side, and then we will solve the equation, whatever the equation we will get. Like it's just bringing all the equivalent parameters to single side, so we will have a simpler network to solve. Or else it's like, let's say there is this transformer and we have, let's say this is LV and this is HV, and here we have some R resistance components, impedance components. Here we have another resistance components and impedance components. Now we wish to eliminate this particular turns in between so that it will be a single circuit, right? So if it is a single circuit, it will be easy to solve. So with this turns ratio, we will refer whatever parameters here to this side, and we will have only single circuit. So this will be supply, and we will have some resistances and impedances. It will be a simple circuit. This will be an easy network problem. So just to make our calculation simpler, we will refer all the components in the HV side. Yes, yeah. you're correct. So we need to evaluate everything in one side. That's absolutely correct. So ZL is given. We need to refer this ZL to primary side. I'm referring ZL as a ZL dash, which is a primary side. Now, how to refer resistances to primary side? You have gone through the lectures, and in the last week also we discussed the same thing. How to refer current, how to refer voltage, how to refer resistance or impedances in either side. Now, yeah, Smith, you are correct. We have to multiply with square of the turns ratio. So just if anyone has any doubt, I'm just writing it again, so they will remember what we discussed. RL dash divided by X. Yeah, turns ratio has been calculated. Sir, in the question it was given, right? The rating of the transformer is 100 by 500 volts. So it is nothing but the turns ratio. The LV side, this is LV, it is HV. LV is 100, and here it is directly the turns ratio. It is 1:5. So this is the turns ratio. A will be 0.2. Yeah. Now I1 by I2 is equals to N2 by N1. Now, yeah, we will divide these two equations. Now just multiply equation 1, V1 by V2 into I1 by I2 is equals to N1 by N2 so I1 by I2 is nothing but N. Okay. N1 by N2, I1 by I2 is N2 by N1. Yeah, sorry. You divide it. What is second equation? This one, current. Yeah, we are trying to get a relation between impedances, because we know voltage and current relation with the turns ratio, but we are trying to refer impedance here. So I'm just yeah, you will see why the second equation came into picture. So N1 by N2 divided by N2 by N1. Now this is N1 by N2 whole square. Oh yeah. So V1 by I1 divided by V2 by I2 is nothing but R1 by R2 is equals to N1 by N2 is nothing but turns ratio, A square. Now, yeah, this what relation we got is R2 is equals to R1 into 1 by A square. Now, let's say R1 is LV side, R2 is HV side. If we want to calculate any other sides, we have to multiply. You have to multiply the whatever parameter you are taking with the turns ratio. Now we got this relation from the whatever we derived it. We got this relation, right? And now we know R2. Let's say R2 is HV side. Now R1 is LV side. A is nothing but the turns ratio. We know the turns ratio. We know the LV side. Now we are trying to refer HV side parameter into primary side. Now, yeah, let's take another sheet. The second equation is voltage and current relation. In a transformer, that's the principle. V1 by V2 is N1 by N2. So now we have just divided those two equations. You are asking that relation between voltage and turns. Okay, I will just say that. Now, let's say now this is N1 and N2. These are the different, current and turns. Coming back. So let's say this is I1. This 2. Now V1 and V2. Now based on this turns ratio, voltage will get divided like V1 by V2 is N1 by N2. Now the amount of voltage that is induced in the second will be the turns ratio into V1. So that's the tapping we know. Now we know everywhere in any the common law is energy balance should be there, right? V1 I1 is equals to V2 I2. Whatever power that is supplied by the primary side should be delivered to secondary side. Power balance is universal law, right? Now, V1 by V2. From this equation only we will get the relation between currents and turns. I2 by I1. Now V1 by V2 is equals to N1 by N2. It is I2 by I1. This is the relation between current and turns. Is it okay now, Mr. Leela Kumar? Sure, no problem. Now the relation we got is R2 is equals to R1 1 by A square. Now we were trying to get the primary side, whatever the load impedance, we are trying to refer it to primary. Now ZL referred to primary, that is here R1, that is nothing but ZL actual, that is load impedance on the secondary side, multiplied by A square. This is the equation from this we got. Okay. Now what is the impedance referred to primary now? ZL is 50 plus J40 multiplied by A. What is the value of A? That is 0.2 square. Okay. Can anyone tell me how much it is? Please calculate along with me so that we can match our answers. Okay. How much? Can anyone tell me? Okay, I will write here the answer I got. ZL. Okay. Right. Smith. We got it right. So correct, Siddhant. Nice. So I hope everyone's getting the same answers. Okay. Now let's draw the entire circuit. Now we have referred all the parameters to the primary side. Now we don't have any parameters which are from different side, HV side and LV side. Now all the parameters are from LV side. Now it's simple. What was the question asked? Now let's see the question what was asked. The LV side is energized with the rated supply. So how much is the rated supply in the LV side? Can someone just tell me what is the rated supply? In the question, if you see, we know how much is the rated supply in LV side. Yeah, correct. Yeah, 100 volts. Now let me draw this circuit. Now we are giving an 100 volts RMS here, and we were asked to find the current here, that is I1. Now what are the values of RE? RE is 0.12 ohm, XE is 0.19 ohm, J, and RL dash, how much is RL dash? 1.6, 2 ohm, J 1.6 ohm, and R naught 130 ohm, and this is 70 ohm. Yeah. Now in order to calculate the I1, nothing but, let's say V1 is 100, I1 is equals to how much? Now if we know the input impedance, Z1, I1 will be V1 divided by Z1. Now what is Z1? Z1 is nothing but this circuit R0 parallel to X1 plus R0 parallel to Xm plus Re plus Jxe, that will be in series with our load side, RL dash plus JXL dash. So please calculate with me and tell me what is the input impedance. I will also calculate. You just solve the circuit, R0 parallel to Xm, we know all the values, and please calculate it. RE. Anyone got the answer? Okay, this Z equation. Okay, Mr. Leela Kumar, this is the last question we will be solving. In this question, we will be solving for LV current, HV current, and power factor, and those calculations will be there. Rest of the concepts will be from 7 o'clock discussion. Yeah. Okay, this Z equation is nothing but the equivalent input impedance in the entire circuit. So, yeah, you see the circuit here, right? So this particular circuit. Yeah, this circuit, you can see R0 is parallel to Xm, and that branch is in series with Re plus Xe, and that branch is in series with the load. So the total impedance seen from the input side will be R0 parallel to Xm branch plus Re Xe plus this one. Yeah. Okay, anyone got any answer? Input impedance, so let me write it. Okay, you calculate it. Let me also write what I got. 100. This is the total voltage, that is V. Now just I'm writing directly to the current. 100 divided by 1 by Z1. 1 by Z1 is nothing but 1 by R0 plus 1 by Xm. That is R0 parallel to Xm. Now it is entirely in series with Re plus Xe. 1 by Re plus Xe plus RL dash plus JXL dash. So, can someone tell me what answer they got? Okay, so better lengthy calculation. Yeah, plus please do it. Okay, someone typed it in the A plus IB form. Let me see. Yeah, that's right. Any more answers? Minus imaginary component, can you check again once? Yeah, let me also do it. Please check your answer, Smith. Okay, please solve it. Okay, I'm just giving the answer here. Please tally with it whenever you get the time. RE plus XE, yeah. Okay, yeah. I think we made a mistake here. See, that's why I'm not able to get it. So this R0 is parallel to XM. That is in parallel to RE plus JXE plus this one. That's where I'm thinking. See, let's say this R0. This is the parallel branch. This is R0 parallel to XM, and this will be in series with RE plus RL dash, and this is XE plus XL dash. Yeah. So this is not in series. So this is parallel branch, and this entire thing is series. So yeah, that's how you do it. This is the equation. Please solve this equation. These two are series, and this branch is in parallel with R0 and XM. Yeah. Please, yeah, Fahid, can you solve for this one? 1 by R0 plus 1 by XM plus this one. Now you will get a different answer. Yeah, so I'm just writing whatever I got here. This is 100 multiplied by 0.28 minus 0.24i. Now the answer I got, I'm writing it in the polar form. That is r at an angle theta, 37.55 at an angle minus 41.08. Okay. Please check everyone. Is everyone getting the same answer or not? It's just a bit lengthy calculation. Please make sure you don't do any calculation mistake. That's very critical. If you have, yeah, how I calculated in polar form. Okay. Let's say you have the equation in A plus IB form. So the polar form will be of A square plus B square at an angle of tan inverse B by A. So yeah, if you have this kind of calculator, now you can calculate in complex form A plus IB, and you can directly convert that into polar form. There is a option here. Yeah. So yeah, this is the LV side current. Everyone please tally. If not, after the session, please calculate and see whether you are getting the same answer. If you are not getting the same answer, just reach out to us. We will see. Now, yeah, that's to move forward to the next question. Yeah, we were asked the LV power factor. Now it's simple because Power factor is nothing but the angle between voltage and current if we have a polar form equation. So it should be very easy for now, because what is the LV current we got? How much? 37.55 at an angle minus 41.08. So this is nothing but the angle between voltage and current. So let's say if our voltage is reference, it is at, our current is at 41.08. Why I drawn why our current is lagging the voltage means it's minus sign. So yeah, this is the angle between voltage and current. So power factor is nothing but cosine of the angle between the voltage and current. The answer is cos of minus 41.08. How much is it? Can someone tell me what is the cos of minus 41.08? Okay, Siddhant got 36.87 minus 40.6. Yeah, close to the actual answer. It's fine. Cos. Yeah, yes, Siddhant, correct. Smith, Dhanesh, yeah, everyone's getting right. So 0.7537. Correct. It's a simple problem, calculating the power factor. Now let's see what the next question is. Now we have to find the HV side terminal voltage. Now what do you understand by HV side terminal voltage? So indirectly we are asked to calculate the load side voltage. Okay, so can anyone tell me how to calculate HV side terminal voltage? Any idea? Just to type it in the chat box, like what's the way to proceed. Okay. It should be simple. Okay, let me just give you an idea here. So let's say V1, I1 are LV side and V2, I2 are HV side. Just for the sake of calculation, LV and HV. Now we already know how much is V1 and I1. V2 is already know, that is secondary side voltage, but we are asked to calculate the terminal voltage. Now let's say load side voltage. Load side voltage is nothing but HV side current multiplied by load side impedance. We already know load side impedance, it is given in the question, and just we have to calculate the HV side current. Now what is LV side current? 37.55 at an angle of minus 41.08. Now, yeah, what is the turns ratio? It is 0.2. We have to calculate HV side. Can someone tell me what is the formula for HV side current if we know the LV side and the turns ratio? Okay. Right. Correct. So HV is equals to ILV multiplied by A. Now 37.55 at an angle of minus 41.08 multiplied by 0.2. Can someone tell me the answer for this? tell me in the polar form what is the magnitude and angle of this is high HV side. No. Shah Tulsi, can you recheck your answer? It's 37 multiplied by 0.2. It should not be that less. And angle also. We are just multiplying with the constant, no? Angle won't change. Yeah. Yes, Siddhant. Everyone just tally the answer we are getting. Yeah. You just calculate the terminal voltage. That is 7.51 at an angle of minus 41.08 multiplied by ZL. How much is ZL? 50 plus J40. Yeah, please multiply and let's see what the answer is. It all depends on the decimals, like how accurate we are calculating. So maybe if you are taking, previously we got here 37.55 minus 41.08. It's not that accurate. We have to take, if we take 3-4 decimals also, this decimal point will change. So yeah, that's why you don't worry about that. We will be provided a range of answers for the answers we are giving in the assignments. Yeah, 480, right? 480.87 at an angle of minus 2.42 something. Is that correct? Yeah. It should be okay. Yeah. Let's see quickly this question. The next question, I hope everyone got the answer. HV voltage, terminal voltage. Yeah. Now let's see the output or load power. Load power, if you see the question, it was asked in the watts. Now we know P is equals to active power, that will be in watts, and Q will be in var, and yeah, S is equals to P plus JQ, where P is VI cos phi and J VI sin phi. So since it is in watts, we just have to calculate this VI cos phi, where it is the load side condition. So you need to multiply with HV side, whatever is the voltage, VL side multiplied by I HV side multiplied by cos phi. This cos phi is the angle between load side voltage and load side current. Or the another way, can anyone tell me another way to calculate the load power? Because it is asked in watts, only the resistance will come. Okay. Imaginary component we won't consider. Okay. I just write here I square R. I square R will also give us the output or load power. RL. Now this both will give the same answer. Let's solve one and you can tally the other one later. So because we already calculated the HV side current, how much we got HV side current? Something, yeah, 7.51. We are taking the magnitude only because, yeah, 7.51 square multiplied by RL. What is the real component in load? 50. It's 50 plus J40. 50 is the resistive element. Now this should be yeah. This is the load power we are getting. Please tally with the answer, and you can also cross verify this answer with this formula. Yeah. You can do that after the session just to check the answers. Correct. Yeah, Danesh. Yeah. Tulsi. Correct. So let's see the last question for today. We have to estimate the efficiency. So what is an efficiency in any system? If we are supplying some power, we are generating some power, how much power is actually reaching the load side? How much power we are able to utilize whatever from being generated? I'm talking in terms of power. That's the efficiency of in terms of power. Now, efficiency is equals to P output by P input. So this voltage will always less than 1. There won't be any 100% efficient system where all the input power is utilized by output power. Some will be losses and all. So yeah, if we calculate output and we have input power, the ratio between output power to input power will be efficiency. Now, can someone tell me how to calculate efficiency here? Because we already know, we just calculated the load power. We know the output power. We just have to calculate the input power. Okay, I'll just write it. Now, P input is equals to V1 I1 cos phi. Yeah, output plus losses is also correct to input, but here we don't know the losses. Hysteresis and eddy current that we have to calculate, whatever all the core losses, copper losses we have to calculate. But the easiest way is we already know V1 I1 cos phi. That is the input side. From the LV side, we are giving voltage input. We already calculated LV current. We know the cos phi. Everything is calculated. So we can directly calculate input. We don't have to go indirect method, output plus losses. Yeah, correct, Danish. So how much is VI? RMS voltage, we already know the input voltage, that is 100 multiplied by I1. How much is the I1? I forgot. ILV. Yeah, here it is ILV. 37.55. Here all RMS only, 37.55. What is the factor? Cos phi, how much we got in power factor? 0.7537. This is input power factor. Yeah. So how much is this input? 100 into 37.55. 0.7537. 2830.1435. Right. Correct. Now the efficiency will be output. What is the output we got in the previous 2820.005? 2820.005. 28. How much is the efficiency now? We are losing around 10 watts to losses here. You can see that from output power and input power. Right. 98.9. Dhanesh, can you check your answer? 98 is not... Yeah. 2830. Yeah. 99.64. Fine. Okay. And yeah, that's all we are going to discuss today. more questions on flux calculations, and rest of the calculations will be concepts will be discussed in the 7 p.m. session. Please join that session as well. There are more concepts which will be discussed in that session. Yeah. So yeah, someone was asking about multiple windings in the transformer, right? So what exactly the problem was? Is just a problem or anything I need to explain in that? Let me just get that as well. I'll just explain it because we are past the time. I will just open up. Yeah, I hope you can see this is the last week. So last week session which we discussed how to calculate I2 in it. Okay, yeah. So here this I2 and I3 we calculated, right? So that I2 is not dependent because we are having two different coils here, I2 and I3. So they are dependent on the load. We know R2 and R3, and we know V2 and V3. Now from there, that relation we have to calculate I2 and I3. When we know R2 and we know voltage, that's how we got that's how we got calculated the current equation. So it's not N2, N3. It's not. We are not giving supply to one winding, and we are not expecting like there is no relation of turns here when it comes to only I2 and I3 here. That was the point we discussed yesterday. So we don't know the relation between I2 and I3 in terms of turns ratio because it is the load dependent. Those I2 and I3 are the load currents. Now to get a relation between I2 and I3, we went to the Mmf Balance Equation where we know what I2, we have two unknowns there, I2 and I3. Now in order to get a relation between I2 and I3, we took the voltage relations. Voltage will be induced based on the turns ratio, but here the currents are dependent on the load. That's why we didn't went to turns relation here. From whatever voltage V2 and V3, we splitted that V2. V2 is nothing but I2 and R2. V3 is nothing but I3 and R3. That's how we got. Here I2 is decided by the load. If we change the R2 and R3, the current will change. Right. It's not, even if for whatever may be the turns ratio, I2 will change if we change the load. Because the load draws that amount of current, it requires different amounts of current for different loads. So that's why we went with that type of calculation. Is it clear now? Let's go how the next slide equation came. You mean this equation 2.5 I2 plus I3? Yes, okay. So this is N1 I1, we know that. It is that equation is nothing but the MMF equation. So I18 is N1 I1. How much is see this equation N1 I1 is equals to N2 I2 plus N3 I3. That is only the equation here. So we have substituted the N1 I1 I2 all the known quantities, and it simplified to that equation. So yeah, this particular equation only. If you this N1 I1 is equals to N2 I2 plus N3 I3. Here we substituted N1 I1, we know N1 I1 value, N2 we know, N3 we know, but I2 and I3 we don't know. That's the equation here. Mmf Balance Equation, that is. So how you got that N1 I1, this equation you understood how N1 I1 is equals to the 2 MMF? Because the primary side you will get the flux in this direction. In the secondary side there are two fluxes that will oppose the main flux. That's why these two fluxes sum will be equal to the primary flux. Yeah, that is after simplification. N1I1 is 900, N2 is 125, N3 is 50. You simplify it, you will get that equation. Okay. I hope it is clear now. Siddhant, you understood how we got that 18? Because N1 and I2, N1, N2, N3 are 50, 125, 100. And R2 is 100, R3 is 75. So after simplification, we got that. Okay. So if everyone is clear with today's discussion about hysteresis loss, eddy current loss, what exactly is hysteresis loss, eddy current loss, and how they are caused, why hysteresis loss is caused because of the movement of the molecules, everything, I hope everything is clear. And the dependency of the losses on voltages and frequencies, how to relate them with equations. Yes, definitely, Siddhant. Actually, last week there was no problem with the microphone. I don't know why this week it came. From next week, I'll make sure this problem won't be there. Sorry for that. Yeah. Then next we got the equivalent circuit calculations. It's a simple networks problems. We have to keep in mind which side we are referring to. And once we refer all the parameters to either HV or LV, we will proceed with the calculations. And finally, we calculated load, power factors, and terminal voltages and efficiency of the system. So that's all session for today. I hope you have all understood today's session, and please do solve the questions in live session along with me, so that you will also get your doubts cleared. And I hope this will help you in submitting your assignments on time and understanding the concepts. Okay, see you all next week. Please do join the session around 7 p.m. today. You will be getting more concepts discussed there. Thank you all. Thank you. Thank you, Danish.